Are now recording. Hi everybody, welcome to today's review session. This is on glaciers, and it's mostly talking about lectures, the last two lectures on glaciers. So one thing I want to say is that there is a quiz coming up, and I actually pushed the deadline for that slightly back from what it was on the syllabus originally, so you have a bit more time for that. I will be doing a quiz-specific review on Monday when I have a review session that day. And the glaciers material is on that quiz. I'll be going over glaciers mostly today. Also, you're very welcome to ask questions while I'm recording. Just mostly saying that to be aware that this will end up in the video that other students can see. Before I get into the review, here's a bit of an update on where we are in terms of the class. I've extended a few deadlines actually from the initial syllabus, and there's a new syllabus that takes into account those couple of changes I've made. So quiz number 2, I will release tomorrow morning, and it will be open until Friday, February 26th. It was originally going to be due this Sunday, but that feels too soon to me, so I'm pushing it back to next Friday. And it's the second and last Gaucho space quiz that you'll have for this term. And as the first, I hate it when that happens. As the first quiz was sort of
I don't have the video on. Oh, sorry.
Oh, it's okay. I just got distracted for a sec. The first quiz was kind of a check-in midway between the start of the course and the midterm, and the second quiz is kind of like that. It will be a 30-minute quiz. You'll get one attempt to do it, very similarly to quiz 1, and otherwise it's very similar in structure. It's going to be 10 multiple choice and true or false questions, and then 1 or 2 short answers that the TAs will grade. So the material covered will be lectures 10 and 11 on glaciers, which is also the subject that I'm going over today, and then lecture 12, the lecture I'm releasing later tonight, which is the first of the Antarctic history lectures. And there is a clip of Encounters at the End of the World, another movie that I'd like you all to watch. It's the first part of the movie, about the first 36 minutes. If you enjoyed the movie, you're welcome to watch more of it. But it's a documentary that I like because it explores the human sides of life in Antarctica, both researchers and then people working at McMurdo Base. And we're sort of entering, most of the rest of the class is going to be more based on human interactions with Antarctica, because we're doing history of Antarctica, and then we're doing global climate change at the end of the class. Material from before the midterm is not on this particular quiz, and lectures 13 and 14, which are coming out next week, and those are the second and third lectures on the history of Antarctica. Those are also not on this quiz. I do want to mention that the final exam will be cumulative, but this quiz is not. This quiz is just on the material that we've covered since the midterm, basically. And there is also a second reading assignment open now. It's due on the Sunday of Dead Week, so I also pushed that back slightly. And it's very similar to the previous assignment, except that you're writing about a scientific journal article that's been peer-reviewed that's actually someone's study, as opposed to a news article. And there's also a lab due this Friday, Glacial Landscapes due Friday, February 19th. And if you haven't started that already, this is actually good reference material for that, because it's on the material we covered last week in class on glaciers. And so assignment number 2 is about a scientific journal article, one that is detailing research and written by the scientists themselves, or possibly the historians themselves, because I am open to those who might be more interested in the human history using more historical or social science-based articles about Antarctica. That is fine by me, but the main thing is that it needs to be an academic peer-reviewed article. And when I say peer-reviewed, I mean that someone else in their discipline who wasn't involved in the project has looked over it for errors and inconsistencies and conflicts of interest, and that is standard practice in academia. Generally, if something is not peer-reviewed, it's considered to be very suspect, because peer review is supposed to be kind of a people who know what they're talking about but who aren't invested in the project are the ones deciding whether it's worthwhile. Of course, that's not completely devoid of human error, but it's meant to filter some of it out. So anyway, most of you are probably going to choose science articles, but history of Antarctica or social science about Antarctica is fine too. For science articles, GeoRef is a really good resource. It's a database you can access through the UCSB library online system. And one thing you can do is just even start by searching Antarctica or Antarctica plus a keyword like Antarctica and dinosaurs or Antarctica and skuas or Antarctica and Shackleton if you're studying history or something of the sort, and you can see what comes up. And the word count and length is about the same. You need to include a link. The requirements for your response, which is otherwise pretty open-ended, are that you have to address what the author's research goals are, and they'll usually put that in the intro. And then also, what are the author's results, and if those results are what they were expecting, which they will usually also say. It does not have to be a long article. In fact, I suggest you don't choose a long article because it'll be much easier to summarize a short one. Any questions about assignments and what's going on in class in the next couple of weeks and the like? Okay, I'll go ahead and move on to some recap material then. So just find a place for that. There we go. So in the first glaciers lecture, we talked first about how glaciers fit into the overall water cycle and how they in fact contain most of the fresh water on Earth. And a lot of that is actually in the specific ice sheets, the big continental glaciers that cover whole land masses, particularly the two ice sheets that cover Antarctica. A lot of lecture one focused on the physical varieties of glaciers. So there's two main ways to categorize glaciers. There's physical shape, which is something I featured more in lecture one. And then there's what I'd call thermal behavior, aka whether a glacier is cold or warm based. So that classification is completely separate from all the terms here. Hypothetically, ice caps and ice sheets can be either cold or warm based. Ice sheet, and the same is true of alpine, cirque, valley glaciers, and the like. It's kind of like describing the texture of something and describing the color of something. Both give you valuable information, but they're separate properties. So we focused on continental glaciers first, and those are glaciers that are not defined by their surrounding topography. So that includes the ice sheets, the largest ones, those bigger than, I think the number was 50,000 kilometers squared. But anyway, but a continental glacier that actually covers an entire continent is known as an ice sheet. So that includes the Greenland ice sheet, which covers most of all of the subcontinent of Greenland, and then the two separate Antarctic ice sheets, the East Antarctic ice sheet, the much bigger one, and the West Antarctic ice sheet. And the colors, this actually is this is a graphic from an article on global warming that is showing ice loss. And you can see that Greenland is all red. Greenland's ice sheet is losing a lot of ice. The Arctic, again, is warming faster than the Antarctic in general. A lot of that has to do with the fact that the Arctic Ocean is absorbing more heat. But that's not something we really went over in this lecture. It's just kind of something I'm pointing out here. Before I move on from that, actually, I did want to mention also that I went over the definition of a glacier, and glaciers are really compacted ice that are moving under their own mass. Glacial ice is different from granular ice, which is kind of the ice that you would get as crushed ice in terms of how much air is present in it. Glacial ice is very compacted to the point that only about 1/5 of its volume consists of air bubbles. And snow, 90% of it is air bubbles, actually. Snow is very light and fluffy because it's mostly air. But as you compact snow, as the snow falling compacts over time, it produces glacial ice, and that will actually slowly move downhill. Because you have to remember, glaciers are moving. Glaciers in Antarctica are actually taking the place of rivers. But anyway, Antarctica has its two ice sheets, and so does Greenland. If you have a smaller continental glacier, one that covers part of the continent, like you have in Iceland or in some of the Canadian islands, you have an ice cap. And then glaciers that are constrained by their topography are considered non-continental. And I do want to point out that there's a lot of fluidity here, because ice sheets in Antarctica, as they approach the coast where there's more exposed mountains, do sometimes kind of turn into alpine glaciers or Piedmont glaciers as they do start to get constrained by mountains. So what a glacier is can really depend on what point along its course you're looking at. We say that we do refer to the glaciers in Antarctica largely as ice sheets because for the most part, they behave as big ice sheets. They cover everything else, but they start to turn into other types of glaciers as they approach the coast, where there's more rock exposed and where you have glaciers starting to flow around mountains through valleys. So alpine glaciers are those that flow down from mountains, and a cirque glacier is a particular type of alpine glacier that you find in a bowl-shaped valley near the top of the mountain, and cirques are often where glaciers start, especially outside of Antarctica, where you have glaciers forming in the mountains but not covering all of the mountains. You have glaciers forming and carving out these bowl-shaped valleys, and remember that when glaciers carve out from underneath them, they make a curved shape because glaciers are larger and shovel more out of their way than does liquid water. As glaciers move downhill, they become valley glaciers as they get wider, and valley glaciers can become Piedmont glaciers if they suddenly spread into a wider valley and the ice begins to spread in all directions. And you do actually see that in Antarctica quite a bit, where ice from the ice sheet starts to flow into the dry valleys and spreads out in there. I saw several Piedmont glaciers while I was there, actually. If glaciers flow to the ocean, they're called outlet glaciers, and one specific type of outlet glacier is a tidewater glacier, where in areas that have high tidal variation, and because tides vary more in some areas than others, which is something we don't really go into here, but in areas with high tidal variation, if there happens to be an outlet glacier going to the ocean, at high tide, the water will provide a lifting force to the glacier. The buoyancy of the water will kind of lift the end of the glacier up, and that will in turn sort of lift the glacier that's further upstream up, and the glacier will flow faster because the lifting force is causing it to be kind of less firmly attached to the ground. There's less friction. But then at low tide, the glacier will sink back down at the end, and then the part of the glacier on land will settle back down on the ground and will experience the usual amount of friction again and flow more slowly. Does anybody have questions about this slide or any of the topics I just covered before I move on? And the material for this lecture, the material for this review session, I'm sort of classifying it, but I'm sort of going lecture by lecture. There's some topics that sort of show up in both of the lectures, and it's not quite as clearly defined as some of the differences between some of the other lectures, but I'm sort of just going in order right now, in order of what I covered last week. So in the second half of lecture 10, I talked about how sort of the course of glaciers. And when I say that, I mean how glaciers move from the center of the continent to the edges of the continent, carrying ice, aka water, along the way. And one thing you want to remember is that glaciers don't, a glacier, even if you're standing on a glacier and you're like at a single point in the glacier, like you're at a relatively narrow glacier, not all of the glacier is going to flow at the same rate. In general, glaciers flow fastest where there is less friction. Glaciers are going to have the most friction underneath them, where they're grinding against the rock, or if it's a valley glacier or another non-continental glacier, on the sides. So it's the ice in the center and on the top that's going to flow fastest, and that actually generates a feature known as an ice stream. The ice that is flowing faster than the ice surrounding it is an ice stream. And the ice streams can actually, in some cases, form ice falls, a frozen equivalent of waterfalls, if the glacier flows over an area where the steepness changes really suddenly. And one thing to think about is that waterfalls erode underneath them, and the shape of the land under the waterfall changes over time. The same is true of glaciers. A glacier that's going down an ice fall at one point in time, eventually the glacier may just erode enough of the stuff underneath that there won't be as much of a steep drop off anymore, and there won't be an ice fall. So that's just kind of a side point to think about. We talked a little bit about how there is some actually liquid water movement in Antarctica, because underneath many glaciers, the high pressure from the massive ice actually it lowers the pressure melting temperature enough that some liquid water can exist. And so we have a good number of subglacial lakes and even some subglacial rivers connecting them. But overall, they're not that well connected and they don't make up that much of the volume. For the most part, movement of water in Antarctica occurs via movement of solid water, aka ice, from the center of the continent where ice is accumulating out towards the coasts. And the interesting thing about Antarctica is that the ice, the glacial flow in Antarctica reaches the ocean and then continues to flow over the ocean. There is enough ice accumulating still on the coast of Antarctica that ice flows out over the surface of water because, weirdly, solid water is less dense than liquid water. That is because of the way that water molecules are arranged, by the way. It's because water molecules are polar, which isn't something we really go over much here. But that ice shelf is the extension of the glacier, continuing to move out over the water. It's being fed by the ice on land. It's an extension of the glacier coming from land, rather than ice that formed over the sea, aka sea ice. So sea ice is formed from seawater freezing, whereas ice shelves are from glaciers flowing out over the ocean. And ice shelves will eventually break up because the ocean does a more effective job of melting them than does the land. So the transfer of heat from the liquid water to the ice shelves causes them to break up into icebergs, undergoing a process known as calving, and then the icebergs float out to the ocean. And remember that ice shelves are generally pretty stable features. Sea ice tends to be more ephemeral and tends to come and go seasonally, but ice shelves tend to be permanent, although with global climate becoming more unstable, that's changing. Where basically what's happening with global climate change is that the overall temperature changes make it so that there's a new equilibrium point. There's a new equilibrium line in terms of where the ice shelf is stable and where it's going to start falling apart. So questions about this slide before I move on. This is about the end of lecture 10, which was the first of the Glaciers lectures. All right, so I'm going to move on here, and I kept this slide in just because I wanted to go over this distinction one more time. So these are this is the classification of glaciers by their thermal properties, and the glaciers can be either cold-based or warm-based, and that's related to the pressure melting temperature. The pressure melting temperature is the temperature at which water melts under different pressures, and that's relevant because the pressure increases as you go from the top of the glacier to the bottom of the glacier, something I alluded to a little bit before when I talked about how the pressure is high enough at the bottom of glaciers that it can allow some liquid water to form. So what happens is that normally, when I say normally, I mean outside of Antarctica, the bottom of the glacier will have some liquid water at it. We'll have a significant amount of liquid water at it, actually more than is present in the small number of glacial lakes you have in Antarctica. Warm-based glaciers are those that occur at high latitudes, or excuse me, at low latitudes, closer to the equator. Glaciers that you find in the alpine regions of, say, the Andes Mountains or the Sierra Nevada or the Rocky Mountains or the Alps, basically glaciers up in alpine regions of temperate latitudes. So the sunlight is strong enough in glaciers that are at latitudes closer to the equator that the surface of the glacier is heated a bit more effectively. The glaciers are going to get colder as you go. They're going to get colder from top to bottom because the solar radiation is strongest at the top. And the average ice temperature is just about going to follow the line for the pressure melting temperature of water. The pressure melting temperature line doesn't change, notice. That's just how water behaves. But this line changes because you have a difference in how the temperature changes at the top and bottom of the glacier. in glaciers that you have in more temperate regions versus glaciers that you have in the poles. In the poles, like Antarctica, the sunlight does a very ineffective job of heating the surface, and the ice temperature actually is very cold to begin with, and it gets somewhat warmer as you go to the bottom because of slightly more effective heating from the Earth. But it actually doesn't really hit the pressure melt temperature most of the time. So most glaciers in Antarctica are said to be cold-based, meaning that they don't have a lot of liquid water at their base lubricating them. They don't have a steady flow of liquid water helping them move along. And that ends up coming into play with how glaciers move, because glaciers can move in one of two ways. They can either slide downhill all at once, or they can deform slowly while moving downhill with the ice crystals rearranging and changing shape. And so the latter method of slow deformation dominates much more in Antarctica because the glacier doesn't have as much lubrication and doesn't just get a chance to slide downhill as much. Oops. I apologize for that. Does anybody have questions about this? This is just the slide from the lecture, but I wanted to put it back in here because it's an important concept. And this is a completely separate categorization from the shapes of the glaciers. So again, a valley glacier could hypothetically be either cold base or warm base. An ice sheet could be either cold base or warm base, and it could behave so in different parts, in different regions actually, because remember that glaciers change a lot as they flow from the center, from their start to their end. So a single glacier at different points in its flow could be warm base versus cold base at different points. In general, cold base dominates in the poles and warm base dominates in more tropical or temperate latitudes.
So warm base, it's like almost guaranteed to be like a lot slipperier,
Yes,
and
precisely.
like cold base is just like stays still, whereas warm base will move.
It doesn't completely stay still. It kind of deforms. It just kind of flows as a fluid a lot more. Like the ice rearranges slowly as it moves downhill, as opposed to just going like sliding all at once. So it's still moving, but it's moving more continuously and not getting a chance to slide all at once. Does that make sense?
Yeah. Okay.
Yeah, glaciers, remember that glaciers are moving. Glaciers are inherently moving under their own weight. So glaciers move in two different ways, and it's intuitively easier to understand basal sliding, which is how glaciers will slide downhill as a block all at once, or you can kind of think about it as a block sliding downhill. And again, it's going to be more common in warm-based glaciers where there's a lot of meltwater lubrication. And so glaciers in Antarctica, they are moving, but they're moving by plastic flow instead, for the most part, where the ice rearranges and changes shape to allow the ice to function like a very thick, viscous fluid, essentially. Kind of like what would happen if you put silly putty on a slope. And actually, we do something like that when we do a in-person glaciers lab to kind of do a very rough approximation of what glaciers are doing. And it's kind of like actually how if you try to flow silly putty down a slope, if you try to make it go over a slope change, or if you stick a spoon in it or something, those are actions that cause relatively sudden stress. Having to flow over a different slope all of a sudden causes the glacier to come under stress, and then sticking an object into it messes with the flow and causes stress. And you can kind of see how with silly putty or with other kind of those goopy substances they sell that are kind of flow but are still kind of sticky and solid, they'll crack under those sudden forms of stress. And that's kind of like what happens with glaciers. If a glacier, say, flows around a corner relatively suddenly, glacially speaking, or if it starts flowing over rough terrain that doesn't erode as easily, or if it flows over a mound, glaciers will experience brittle failure. The stress kind of comes on too quickly for the glacier to respond with plastic deformation. A glacier, you could think of it as generally happier with the ice just rearranging, because if it's moving plastically, the ice isn't breaking into cracks. You're not getting cracks and thus crevasses forming. But under sudden stress, the ice doesn't have time to rearrange and a crevasse forms. And crevasses actually kind of come and go with a glacier's evolution. Like, for example, if there was a mound under the glacier and then eventually the glacier just completely eroded that mound away, an area that once had many crevasses would no longer have as many. And it doesn't always happen on that quick a time scale, but scientists have to monitor where crevasses are because things can change with glaciers. And one season, an area that was previously relatively smooth can suddenly be full of cracks. And even if they don't understand why, they need to know it's there because you do not want to fall in a crevasse. The other thing on this slide is that I talked a little bit about the concept of ice mass balance and how glaciers there's an equilibrium line that defines the area in which glaciers are getting bigger or accumulating, and the zone in which the glacier is overall starting to break up. And we study equilibrium lines because if they move, that gives us a sense of whether the glaciers are expanding or retreating. The accumulation zone is going to be more uphill where you have snow in the mountains or in the center of Antarctica, causing the glaciers to pile up. And that's actually to some extent what helps the glacier continue to move. The ice flows from the area where it's piling up so that there's too much downhill to where there's not as much. But past the equilibrium line, further downhill, you will get in an area where the influx of glacial ice from uphill is outweighed by the loss of ice to evaporation, melting, sublimation, or calving, when the ice just kind of falls off in chunks. And the reason that Antarctic glaciers go over the ocean is because the zone of accumulation actually extends as far as the coast in Antarctica, which is normally not the case. It's not the case in Greenland, which is why I had a small diagram that showed you how the ice sheets in Greenland tend to calve and break up right along the coast, whereas those in Antarctica flow over the ocean more and create ice shelves. Any questions on any of this? The last subject we lingered on was erosion in Antarctica, which is mostly dominated by glaciers. Aside from a little bit of wind erosion, I did talk about ventifacts and how you get some interesting features carved by wind, especially in areas like the dry valleys where there aren't many glaciers. Wind does a lot more erosion than liquid water because there is very little liquid water present ever. I think I saw liquid water once when I was in Antarctica. There was one time when I saw a stream of liquid water flowing from a small frozen lake, and I thought I was losing my mind for a second. I thought I was like having a dream in the day because it's like I have not seen liquid water outside of my canteen in quite a while. So occasionally you get some meltwater in Antarctica, but not much. So in the areas where you do have glaciers, the glaciers do the erosion. And the glaciers erode in two ways. The first, the more complicated method is plucking, which is actually caused by a change in the glacier. The glacier changes from being a warm-based glacier to a cold-based glacier all of a sudden, and that change is what causes the rock to be ripped away. Plucking often happens when you have glaciers flowing over a more resistant mass of rock. And as the glacier is flowing over rock that it cannot easily grind down, that's going to build the pressure up, and the buildup of pressure is going to produce more liquid water, which is going to help the water move along. Then what's going to happen is that the glacier is going to pass that mass of resistant rock, and all of a sudden that force that was basically stressing the ice out is gone all of a sudden, and the pressure drops really suddenly. When the pressure drops really suddenly, you can no longer have liquid water because lower pressure means that you need to be at a higher temperature to have liquid water. So that meltwater freezes, sort of sticking the glacier to the rock. And the glacier, which is still moving forward, kind of pulls the rock with it. I was going to say the glacier is kind of moving forward quickly. It's not happening that fast. You would kind of see a glacier peeling. It would look like a glacier is kind of peeling the rock away in slow-mo, and that's what basically is happening. But a lot of the larger pieces that you find in glacial debris end up coming from this when you have just large chunks of rocks pulled off. Otherwise, glaciers do what is called abrasion. The movement of the glacier over the rocks slowly grinds the rock into tiny pieces. And glaciers produce a number of a number of different products of erosion. They carry stuff on their surface, which is known as ice-rafted debris. Most of the sediment deposited by glaciers is till. Till becomes diamictite when you lithify it or turn it into a rock. And till is mostly fine-grained. It's mostly the really well ground up stuff that was carried underneath the glacier, but it also has a mix of larger pieces carried along by the glacier and pieces and stuff that was just sort of bulldozed in front of the glacier, because glaciers do just sort of clear everything out of their path. They are very effective at eroding away the land underneath them, because solid ice can crush away at rock actually much more effectively than liquid water can. And again, that's why glaciers tend to form U-shaped valleys. They tend to carve out much more to the sides than does liquid water. So if a glacier ends on land, where it ends on land is going to be marked by a mound known as the terminal moraine. This is the terminal moraine, and it consists of till that's been deposited by the glacier. Some of the material, some material gets carried by the water that's melting at the end of a glacier, and that's known as outwash. And that tends to be very fine clay with some sand. So much more tiny particles overall. In some cases, outwash can form a pattern called varves, where you have a glacier feeding into a lake. And during the summer, when there is more meltwater coming from the glacier, you have layers full of quartz eroded by the glacier. You have lots of glacial outwash, so you have a thick layer of lighter colored sediment. And then in the winter, when the glacier doesn't melt as much, you just have lake mud, darker, organic, rich lake mud. And you see that alternating pattern of light and dark as in the rock record, and it can be a good sign that this lake was in an area that glaciers were feeding into it, which means that there were glaciers there. So varves are quite useful for finding the past record of glaciers. I talked about glacial flour, which is when you grind quartz down to silt size, it gets suspended in the water and actually colors the water turquoise, which is why you see that in lakes in places like Alaska and Siberia, as well as even the ocean in Iceland in some cases. And then you have erratics and dropstones. Erratics are when you just have rocks that are left behind by glaciers, boulders that have just been carried on the surface, and you often find them in an area that was recently glaciated, but where the glaciers have retreated from. The glaciers have just left large boulders that they carried behind after they melted. And in cases where glaciers go out over the ocean, like in Antarctica, they can plop drop stones out into the ocean. Large rocks carried on the underside of glaciers out to sea will fall when the glacier or iceberg melts, and they will fall into the sea mud, which is very fine-grained mud and looks very different from the drop stone. So the drop stone sticks out, like in this picture. And if you see that in the rock record, it's very good evidence that the area under study had glaciers at that time. And that, in fact, was one of the big important bits of evidence for continental drift. They found drop stones in sediments in the rock record in South America and in Africa. And this is a feature that you see when you have glaciers that are going out to the ocean. You have enough glaciation that you have glaciers at sea level. So any questions about glacial erosion? Okay then, so I'm gonna go ahead and shut the recording off in a second and just open things up to questions. This, by the way, is an iceberg surrounded by sea ice. This is a picture I took from a helicopter. And it's a good example of how the two are different. This is an iceberg that was broken off from the Ross Ice Shelf that is now surrounded by the sea ice that's formed around it. So it's ice surrounded by ice, but this is ice that came from the land and then eventually broke off. And this is ice that actually froze out over the ocean. All right, and recording stopping in just a sec.